All right, in this video we're going to look at solving trigonometry equations, which is a neat little exercise that brings together some graphs and our knowledge of the symmetry of the unit circle and basically everything up to this point. It's not as onerous as previous solving on like polynomials and all that sort of stuff because we already know the answers to these ones. So questions might look something like this. We're looking for sine theta equals a half, given that theta is an element of 0 to 4 pi. All right, now, incredibly important information is this. All right, we've already seen in the sketching and the graphing that the graphs just stretch into infinity unless we're given a domain. All right, so sine graph just keeps going and on and on and on and on. Obviously, when I'm solving, I need to know some set values, so I need to know a domain. Okay, so 2 rotations will bring me to here. So this is the domain that I'm looking for solutions for this equation here. If I don't have that domain, I have to generalize the answer and somehow list all possible infinite solutions, which is quite difficult. Okay, so let's jump in. We'll erase this second half here. All right, now I'll erase the whole lot because the first information we want to do, and what I always advise people to do, is to do a quick sketch so we know what we're looking for. So first of all, axes, sine graph. That's a terrible point there in the second one, but we'll just go with it. All right, so there is my domain across from 0 to 4 pi. All right, now we know that it equals a half. Okay, now this is a sort of a cheaty way of doing it. This is a y value. I treat these as simultaneous equations. So here's the purple one, and I'll graph the red one at a half. So I just put a dotted line through here. And you can see that I'm looking for the x values at that intersection point, that one, and that one. So you can see if this quick sketch is correct, I'm looking for 4 solutions because it's from 0 to 4 pi. Based off what we know already of the unit circle, we know that sine is positive in 2 of the 4 quadrants. Sine is positive in the second and the first. All right, and given that this was positive a half, that would mean that we've got 2 solutions in the first rotation, and then because it's 4 pi, we go around again, and we get 2 more solutions in the second rotation. All right, so that sits with what we can see here in the sketch. Okay, now it's just a matter of working out what we need to know to find the x values. Okay, so on your calculator, what you do is something like this. Equals theta, making sure that your calculator is set to radians. If you don't have a domain specified, then it will spit out a general form, which is not very helpful. So your best bet might be to define this across the given domain, 0 to 4 pi, and then solve it like this. However, we can do it based off what we know. We know that the exact value for which the sine is a half is in radians is pi on 6. We know that pi on 6 is the first quadrant angle here. All right. We know that the first quadrant is 0 plus pi on 6. The second quadrant is pi minus pi on 6. So there's solution 1 and solution 2. So the answer here is pi on 6. And then pi minus pi on 6 is 5 pi on 6. So there are my first 2 solutions. To reach the next 2, I just add 2 pi to each of them. So 2 pi plus pi on 6 is going to give me 13 pi on 6, and 2 pi plus 5 pi on 6 is going to give me 17 pi on 6. If you're not sure how I got them, 2 pi on 1 converted to over 6 is going to be 12 pi on 6 plus 5 pi on 6, and that makes 17 pi on 6. And the same for the first one, 12 pi on 6 plus pi on 6 is going to give me 13 pi on 6. So now I can list my 4 solutions in order from smallest to largest. 5 pi on 6, 13 pi on 6, and then 17 pi on 6. And those are all the solutions that we've been asked to find, and you must list all of them. All right. it's incredibly important that we refer to all the stuff we've done here. So looking at the domain, doing a quick sketch, identifying how many solutions we are being asked to find, confirming it on the unit circle, then going through our exact values based on the sine or the cosine given to us, and then converting that into the required number of solutions. All right, so there's it's a detailed list of steps that you need to go through, but it should make sense, hopefully, based off what we know. To give it another bit of practice, what happens when we are not dealing with exact values, such as this one here, sine x equals minus 0.3. All right, and it says the domain is 0 is less than x is less than 2 pi or equal to or equal to. All right, so I've got one rotation. So this quick sketch here is going to look like this. All right, I've got negative 0.3, so it's going to be down here somewhere, and I can see from my graph I'm looking for two solutions, which fits with what I know of the symmetry. Sine is negative in quadrant 3 and quadrant 4, so that should be two solutions. All right, so now, because it's not a nice exact value, I'm going to have to work with what I know. All right, so what we know is that on the calculators, the inverse of the 0.3 minus 0.3, sorry, will give me an angle, 0.30469. This is the first angle in the first quadrant. So that's not going to help me here. I need to know how to convert that into third quadrant angles and fourth quadrant angles. To convert it into third quadrant angles, we know that it's pi plus the angle. And fourth quadrant angles is 2 pi minus the angle. All right, so you can see here that we've found out what the angle is in the first quadrant and converted it into the required quadrant, given that we knew there was a negative result. Okay, so this pi plus will roughly equate to 3.446, and this 2 pi minus will roughly equate to 5.978. Okay, now given this is the angle that we're looking for in radians, so it's 3.44 radians and 5.978 radians. If we look back at our solution, our sketch, we can see that we wanted two solutions. We've found two solutions right there. Okay, so we could finish off listing both of them from smallest to largest, and that is it. So to recap, in both of these examples, it was very important that we knew that the result of the sine or cosine value, whether it was an exact value or a decimal, we need to know which quadrant we're looking for the solution in, whether it's negative or positive. We need to know how many solutions we're finding. If we need to use the calculator, we do that, and we also need to remember how we can get into each of the quadrants without having to start from the start and go around. So quadrant 3 is pi plus, quadrant 4 is 2 pi minus, quadrant 2 was pi minus. All right, so those are things you need to have written in your books so that you can refer to them as you go through. On to a little bit more complex examples. We also might be asked to solve equations like this, where the angle is not on its own, so it's 2 theta here. All right, and theta, given that theta is element of minus pi to pi. All right, so I've got a compound angle. I call them compound angle. I'm not sure if that's the correct term, but it makes sense to me. So a quick sketch here of sine 2 theta is going to be 2 pi would have been there, pi would have been there. I've got the domain says I start from negative pi, so that's out here. All right, negative pi. So I would have had, if I'd drawn this nicely, it would have been like this. This is a terrible graph. Looks like waves and not what I want it to. Anyway, this is the domain down here. All right, so the domain is inside the purple lines. You can see there that I'm looking for minus root 3 on 2. I don't have to put it in exactly, but it's going to be down here somewhere. So I'm looking for 4 solutions there, 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 and there. Okay, so 4 solutions. Now the way to treat this is to do something a little bit sneaky and just say, I don't like having a compound angle. Let's just solve this equation here. All right, we know that that's an exact value. We know that the answers are going to be nice there. Because I've substituted this out, x in place of 2 theta, what I need to do is to change the domain. I'm going to change it, instead of being from minus pi to pi, I'm going to double it. So it's going to be minus 2 pi to 2 pi. And I double it because that was the coefficient in the initial problem. All right, so that one has to be the same. Okay, so now I'm looking to solve this equation. But this equation has slightly changed. So let's do a quick sketch again. Oops, I'll make that a black line. Quick sketch. Oops. Both directions, it goes from minus 2 pi to 2 pi. You can see here that it's going to have the same number of solutions. It's going to have, if I put in the minus root 3 on 2, you can see that it's going to have 4 solutions still. All right. When I account for this change at the end, because whatever I've changed at the end, I changed here, I have to account for at the end, it's going to bring it back to make it look like the initial sketch. So just bear with me and you'll see the process come to light. All right. So it was looking for 4 solutions still. We know that the solutions where sign is negative are in quadrants 3 and 4. So I'm looking for pi plus and pi minus. To know that, I need to know the angle. So I need to know that the exact value for sine is sine of root 3 on 2 is x should equal pi on 3. So that's the first quadrant angle, is pi on 3. So now I use that to calculate the third and fourth. So I have pi plus pi on 3 and 2 pi minus pi on 3. Now, that is those 2 solutions in the positive domain of the function. How do I get to the other 2, which are in the back end or behind here? So we can just use our knowledge of the symmetry to calculate this one. You might notice that the first solution backwards is just 0 minus 3 pi, pi on 3. And then the second solution backwards is going to be the halfway point plus pi on 3. So that's negative pi plus pi on 3. All right, so we've got our 4 solutions right there. So pi, first one, pi plus pi on 3 is 4 pi on 3. 2 pi minus pi on 3 is 5 pi on 3. 0 minus pi on 3 is minus pi on 3. And minus pi plus pi on 3 is minus 2 pi on 3, or 2/3. All right, so 1 pi, take away a third of pi is 2/3 of pi, is a good way of thinking about it. Now, this is what x equals. You'll notice up here that x was the angle we substituted out in place of 2 theta. So now I have to bring that back. All right, so instead of x, I need to know what theta equals. To find theta, I would just divide each of these by 2. Okay, dividing each of them by 2, the shortcut is to double the denominator. So 4 pi on 6, 5 pi on 6, minus pi on 6, and minus 2 pi on 6. And then simplify if we can. You'll notice that 4/6 is the same as 2/3, 2 pi on 3. 5 pi on 6 can't be simplified. Minus pi on 6 can't be simplified. And 2/6 simplifies to minus pi on 3. So here are my 4 solutions. All right. I haven't done anything fancy, but you'll notice that each of these is inside the original domain, even though halfway through we changed the domain because we changed the angle. All right, so if I account for that at the very end by dividing by whatever the coefficient was, the angle solutions drop back inside the original domain. The last step is just to make sure I write them in ascending order so that it seems most logical. It's not strictly necessary, but it makes the most sense. All right, so here you see the process we go through to solve an equation that has what I call a compound angle, or an angle that's made up of a coefficient and an unknown. We substitute it out in place of an easier angle, change the domain by the same coefficient as the angle, solve that problem, and then divide by whatever the coefficient was to bring it back inside the given domain. Lastly, you do want to make sure, just a visual check, that they are inside the domain that was required. So minus a third is definitely inside minus pi, and 5/6 is definitely inside positive pi. So all of the rest are inside the right domain. All right. Lastly, to do this on your CAS, you need to use the solve function again, but you will also, as I said at the start, because these unit circles are infinite, whatever solution you write, or whatever equation you write, you do need to use the vertical line to put in the domain so that the calculator only spits out the certain number of answers required. Right? You can change that domain to be whatever you want, but if you don't have it in there, it'll spit out a general formula for calculating the solutions. It won't give you the exact ones.